Good afternoon, ladies and gentlemen. I'm Roy Salgado, a research and development engineer working at INRIA, France, and today I'm presenting our IWST article which discusses the need for having a system for processing and storing data that provides guarantees on traceability of origins, integrity validations, and the capability of revoking data. In order to introduce the need for this system, we start by presenting the following motivational scenario on patient monitoring and medical record keeping. We have a patient who suffers of a cardiac affection, potentially fatal, so he must wear constantly a heartbeat monitoring sensor, which is constantly submitting his vital signs measurements into a data storage and aggregation server. The cardiologist who treats this patient connects to this system once per week in order to check the evolution of the patient and to check on whether he is responding well or not to the treatment. A caring family member of the patient also carries an app on his or her mobile phone that will notify about a dangerous anomaly such as a tachycardia before an imminent cardiac arrest. In addition to this soft real-time monitoring use case, you also have in this scenario the problem of medical record keeping itself. This very same patient is attended by the medic in a hospital, and the hospital takes care of actually hosting the medical records for the multiple patients that are treated by their medics. It is a crucial responsibility of the hospital to safeguard the privacy of its patients, and according to some laws such as the GDPR, patients may demand the destruction of their private records in hospitals that are no longer treating them after several years. And finally, we have the health insurance company who also needs partial access to the medical records for paying the medical consultation, surgeries, and prescription logs. Although, before performing their payment, they want to ensure that these services are actually needed, and that there's an actual medic requesting for these services. From the previous scenario, we formulate the following problem statement. How do we model, design, and construct a data storage and processing system that supports traceability of origin, integrity verification, and revocation of data? Constructing a system that guarantees this property is important to facilitate the following use case scenarios. First, a clinical trial for a new drug that requires extensive traceability of origin in the gathered data to facilitate verifying the validity of its results. The medical record keeping scenario that was previously explained, and the accounting system of a company that needs to deal with bookkeeping processes where data deletion is forbidden and extensive traceability may be mandated by local tax services and the shareholders. Now we will give our definitions for these three different aspects that we have to guarantee along with our proposed solutions. In terms of traceability of origins, we define it as being able to answer these following questions for each piece of data. Who wrote this data? When this data was written? And with which and whose permissions this data was written? For answering these questions, we make the following observation. These are all questions about the data manipulation context. This observation implies that, first, these questions must be answered at the beginning of this context. Second, we can intercept data accesses and writes during this context by using slots. And third, we call this context a transaction. We model these transactions by using Pharo blocks. Then, we define integrity validation as the process of simultaneously checking these three different Boolean properties on the data. The structural consistency predicate tests on whether the data conforms to a specific schema or not. We define this schema through type annotations that are specified via slots. The domain-defined constraint predicate is composed of the set of additional Boolean predicates that are specific to the business logic that cannot be encoded through types annotations. These are encoded through assertions in the data. The bit level correctness predicate tells us on whether the actual bits that are encoding the data are not suffering from some corruption due to the storage or transmission medium. This can be implemented through checksums or by using cryptographic hashes and digital signatures to provide additional guarantees on data authenticity. To simplify the aspect of checking these Boolean properties, we want to use immutable data structures as much as possible, but we also want the convenience of manipulating data through normal Pharo objects. We achieve this through automatic data deserialization and serialization during transaction boundaries. And finally, we have the capability of rebooking data that our system has to provide. For this problem, we distinguish two different cases of data revocation. Invalidation of data, where the old version can be accessed and read, but the system tells you automatically which pieces are invalid, and the case of data destruction, where the old version cannot be accessed anymore, typically for confidentiality reasons. This is a difficult problem because the data that depends on the invalid data may produce a cascade of further invalidations. For this reason, we have not yet solved this problem. Now we will present our demo. Here we have a demonstration of the patient heart rate monitoring scenario that was presented as a motivation. On the left side here, we have a simulation of the patient heart rate sensor. Since this is just a simulation, we are actually generating a random strip of data that's oscillating around a fixed value, because we don't have an actual heart rate sensor to our disposal. Here we have the dashboard that the medic uses for monitoring his patient. By clicking on it, we can obtain a plot of the whole patient monitor samples, and here on the right side we have the UI that the caring family member of the patient has on an app on its mobile. This UI only displays a single heart rate sample, this one, and a color that notifies on whether he is okay or not. And here we can see it again. A new plot of the plot. Our patient unfortunately is dead now, but since this is a demo, we are going to take a look on how this is connected. So the sensor monitoring process performs its data submission by batches in order to avoid overloading the server with requests. On each batch of data, for submitting each batch, we connect to the data store with the role of the heart rate sensor and perform a transaction where we get the last version of the patient data, and we append our samples, the new samples of the whole batch, into the list of headed samples, and then we commit the transaction. This one, the headed sensor, he periodically performs a transaction only for fetching the last list of samples, and we are actually only interested on the last sample. If it's different, we reload our URI. Then reload, we select the color according to the sample value. As for the medic UI, we fetch the whole dataset by performing another transaction and read the last value of the samples, and at the end we just plot it by using Russell. Since there are no new samples, it should use the same plot. Our main limitation in our current implementation is that we are still not supporting the capability of rebooking data. We are also only supporting a single in-image data store, which is not suitable for long-term persistence. And we are also missing support for distributed transactions. So, we presented a mechanism for modeling and storing data with traceability of origins and integrity validation. We described the issues of implementing data revocability. For solving these issues, we want to explore the following two strategies for implementing revocation in an append-only store that is mandated by the usage of immutable data structures. For the case of invalid data, we just write an invalidation tag into the data store. And for the case of data structures, we always encrypt the data that can be destroyed and generate a unique decryption key that we store to read it. And then, when we want to destroy the data, we just forget this key permanently. And finally, we want to implement support for distribution and to support transactions across different nodes. This is a work in progress. Thank you.